Today we're going to take a look at some applications of the calculus that we've developed, and the first application is economic in nature. So we're going to talk about firms that produce and sell products, and these firms are very interested in three quantities that describe that process: revenue, cost, and profit. As we discuss these quantities, we will assume that the company produces one product and all of its revenue comes from selling that product. So our functions: R of Q is the revenue a company obtains for selling Q units of products. So that's what Q is always going to be, which is the amount of product involved. Revenue equals price times quantity, or R equals P times Q, where P is the selling price per unit of product. So the basic idea here is if I sell 10 units of product at $40 a unit, I get 40 times 10, or $400 of revenue from doing that. C of Q is the cost a company incurs to produce Q units of products. So if you're going to sell something, it needs to come from someplace, and we're assuming the company here produces it. C of Q tells you how much it costs the company to produce Q units of product. And now the thing that the company is really interested in is P of Q is the profit that a company realizes for producing and selling Q units of product. So we're assuming here that Q units are produced and Q units are sold. And the profit is the difference between the revenue and the cost. Revenue is what you take in, cost is what you have to shell out. The difference is your profit. So P of Q is R of Q minus C of Q. So let's take an example. Easton Widget produces and sells Q widgets. Its cost function is given by C of Q is 4,000 plus 260Q plus Q squared. Units are dollars. It sells widgets for $400 each. So the first question is, what's the revenue? And if you remember, revenue is price times quantity. Price is $400. It's selling Q widgets, so its revenue is $400Q. What is the profit? Well, the profit is going to be revenue minus cost, which is 400Q, which is your revenue, minus 4,000 plus 260Q plus Q squared, which is your cost function. We do a little algebra, and we get 140Q minus Q squared minus 4,000. And it can be rewritten as minus Q squared minus 140Q plus 4,000. For what values of Q does the company break even? Okay, so this is a theoretical calculation. A company is not going to want to operate at zero profit, but this tells us what those values of Q are, where that happens. And what we'll do is we'll take this form, set it equal to 0, and factor it. So we get 0 equals minus Q minus 40 times Q minus 100, which is how this thing factors. And you can see that when Q equals 40 or Q equals 100, the profit is 0. And those are the two values of Q which are break-even points. Suppose Q is 50, which is between those two break-even points. What does C prime of 50 tell us? Well, first, let's look at the units of C prime. C prime of Q is dCdQ, which is instructive because it's written so that we can really see what the units are. The units for C are dollars. The units for Q are widgets. So this quantity, C prime of Q, is in dollars per widget. Now we look at the differential approximation. dC is C prime of 50 dQ, which tells us approximately how much C changes when we change Q from 50. So if we set dq equal to 1, dc is approximately the change in cost when we produce 51 widgets instead of 50. And dc is thus c prime of 50. So c prime of 50 is approximately the cost of producing the 51st widget if we've already produced 50. C prime of q, which also goes by notation MC of q, is called the marginal cost. It is approximately the cost of producing widget q plus 1 if we've already produced q of them. Or more generally, the cost per widget of producing the next few widgets after q if we've already produced q of them. Its units are dollars per widget. In this case, we take the derivative of c, and we get 260 plus 2q, so c prime of 50 is 260 plus 100, or 360. Thus, widget 51 should cost about $360 to make. The exact cost is actually cost at 51 minus cost at 50, which when we do the calculation ends up to be $361. So this is a reasonably good approximation. R prime of q, also notated MR of q, is called the marginal revenue. It is approximately the revenue gained from selling widget q plus 1 if we've already sold q of them. Its units are also dollars per widget. Here, since R of q is 400q, R prime is 400, which is a constant. This is no surprise because the selling price is constant at 400, so we should get $400 extra for each widget we sell. And P prime of q is called the marginal profit. It is approximately the profit gained from producing and selling widget q plus 1 if we've already produced and sold q of them. And when we do the calculation, the derivative of P of q is 140 minus 2q, so P of 50 is 140 minus 100, or 40. Its units are also dollars per widget. Thus, the company can expect an increase in profit of about $40 from producing and selling the 51st widget. Marginal analysis is an important technique in economic theory. It has widespread applications beyond what we've just talked about. We return to our consideration of position, velocity, and acceleration. So to remind you, if we have a graph of position, which is in meters, in the positive direction from the origin, and t is in seconds, this curve represents the position of the object at any given time. The slope of the tangent is going to be change in position over change in time. That's in meters, and t is in seconds. And that slope is the velocity, which is the derivative of the position, and the units are meters per second. If the velocity is positive, that means s of t is increasing, and if the velocity is negative, that means that s of t is decreasing. So if we look at this picture at time 1, you can see the slope is negative, which means that s is decreasing, which means that your object is actually getting closer to the origin. At t equals 2, our slope is positive. We can see that s is increasing. The object is moving away from the origin. T equals 3, slope is positive and is in fact actually bigger than it was at t equals 2, so we're moving away from the origin and we're doing it faster than we were. At t equals 4, again we have a positive slope, but it's somewhat less, so we're moving away from the origin, but not quite as quickly as we were doing it at time 4. Now another quantity we want to consider is acceleration. Acceleration is the derivative of velocity, which is the second derivative of position. Change in v over change in t, meters per second divided by seconds, which means that a of t is measured in meters per second, which we sometimes say is meters per second squared, and That's notated sometimes as meters over seconds squared. A of t greater than 0 means the velocity is increasing. A of t less than 0 means that v of t is decreasing. Now we're going to use the tools that we've developed to solve a problem that we couldn't do previously, which is suppose that somebody gives us the position function. How do we calculate the total distance traveled between 2 points in time? The position of an object is given by s of t equals 2t cubed minus 3t squared plus 10 for the time period between t equals minus 2 and t equals 2. What is the total distance traveled by the object during that time period? Now, it's important to realize that the answer is not simply going to be where the object ended minus where the object started, because if I travel a mile to the store and a mile back, I have traveled 2 miles, even though I started and ended in the same place. So we will have to account for turning around and count every distance traveled as positive. So we start by computing the velocity, which is the derivative of position. And here we get 6t squared minus 6t. The next thing is to find the t-values where the velocity is 0. And that happens when 6t squared minus 6t, which is 6t times t minus 1 equals 0. And we can see that happens when t equals 0 or when t equals 1. Now we want to determine where s of t is increasing and where s of t is decreasing. We'll need this so that we count both pieces of the path as positive distance. So what we do is we draw a sign chart for s prime of t, the velocity. We note that it's 6t times t minus 1. So when t is bigger than 1, both of these terms are positive, and we get positive for s prime of t. Between 0 and 1, 6t is positive, but t minus 1 is negative, so that product is negative. And then over here, between 0 and minus 2, both of these terms are negative, so the product is positive. And we conclude here, positive means going forward, negative means going backwards. So we can see that s of t increases between minus 2 and 0 and between 1 and 2. So the object's moving forward. And s of t decreases between t equals 0 and t equals 1. The object moves backward. So we take a look at our chart and we draw a path diagram. And what we'll need is the position of the particle at important points, and those are going to be the endpoints. And our 2 points, 0 and 1, which apparently from the picture are places where the path turns around. So we start by computing s of minus 2, which is minus 18. S of 0 is 10. S of 1 is 9. And s of 2 is 14. Now we start at the beginning of the time interval, t equals 2, and we're at position minus 18. We move right to where we are at t equals 0, which is s equals 10. Now we're going to move left to t equals 1, which is s equals 9, and then we're going to move right again to t equals 2, where s equals 14. And that's a complete description of the path. Now what we're going to do is measure the length of the 3 parts of the path. First, from minus 18 to 10 is 28 units. Next, from 10 to 9 is 1 unit, and then from 9 to 14 is 5 units. When you add those up, you get 28 plus 1 plus 5, which is 34 units, which is the total distance that the particle traveled.